Hi everyone, my name is Celso de Oliveira, a PhD student at the University of Connecticut and a researcher at the TIDC UTC under Dr. Ramesh Malla supervision. Today I will present my poster regarding the dynamic study of Devon Railroad bridges span 70 using a laser Doppler vibrometer. Most of New England railroad bridges were designed and built over a century ago using outdated materials and codes. This make it imperative to understand the current dynamic behavior due to the actual loading and vehicle type to ensure the bridge and user safety. Figure 1 shows the pictures of the span 7, the elevation, and the deck respectively. This poster presents the typical bridge vehicle interaction study of the span 70 of the Devon Railroad Bridge located in southeast Connecticut. The specific objective of this presentation is to discuss the detailed method and procedure to record the field data of the service train using a laser Doppler vibrometer and the process to extract the dynamic parameter of the data. Devon Bridge is located over the lower Housatonic River between Milford and Stratford. It was built in 1906 and it's owned by the Connecticut Department of Transportation. It's a combination between the deck girder, Baltimore trusses, Chiser rolling lift bicycle. The span 7 is a Baltimore steel truss with approximated 218 span length and is adjacent to the east abutment of the South Bridge. Figure 2 shows the schematic of the bridge on the left, where we can see the P1, one of the reading points. And on the right side, we have the finite element render in 3D. The vehicle is the 8th generation of the Metro-North Railroad Company dedicated passenger train. It's an electric multiple unit railroad car with 85 feet in length and 10.5 feet wide, as shown in the figure 3. And the typical composition of the service train is 8 cars. A laser Doppler vibrometer, or LDV, it's a scientific non-contact measure device that uses the laser beam to extract the frequency from the Doppler shift of the reflected laser beam during the vibration of the measured surface. Figure 4 shows the principle of the vibrometer. The characteristic of the vibration is contained on the reflected beam combined with the reference beam and demodulated to derive the velocity time domain of the vibrating target. Figure 4 shows the two types of the vibrometers that were used during the field test. First one is the 3D laser scan, the PSV 500, which was used to record the harmonic vibration of using the shaker. And the second one is the single point vibrometer Vibroflex Q-Tech that was used to record the force vibration due to the moving train. The figure 5 shows the equipment set up during the field test. On the left side, the single point vibration, and the right side, the 3D compact laser scan. The recorded velocity time domain was filtered, normalized, and integrated into the displacement time domain. The figure 6 showed the data processing step and the insert of the vertical displacement time domain of the P1. The natural frequencies were identified using the FFT which stand for the fast Fourier transform from the Vibrometer data. The table on figure 7 showed the comparison between the record data and the finite element modeling. First natural frequency, first natural frequency. The figure on the right showed the mode shape of the first natural frequency. The bridge dynamic behavior recorded using the LDV has maintained the consistent result. The data collection process has proven to be efficient. In addition, the bridge vehicle interaction from the field test and the finite element model held consistency. Updated final element model is under development. This project will enhance the railroad safety by understanding the old bridge's dynamic behavior and the benefit of the vibrometers in the bridge monitoring campaigns. Our acknowledgments goes to the Transportation Infrastructure Durability Center at the University of Maine, the 2018 Region 1 US DOT UTC for partial fund this project, Connecticut Department of Transportation, and the Metro North Railroad Company for continued support and providing the access to the bridges. Polytech Inc. for providing the equipment and the software for the field test. Thank you.